Hi everyone, myself Navyatha working as Assistant Professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. Today I am going to discuss about the topic normalization. The overview of my presentation includes the types of normal forms, and we have already discussed about 1NF and 2NF. We have completed the explanation about first normal form and second normal form. In today's session, I am going to discuss about 3NF and BCNF, Boyce-Codd normal form. So let us discuss what is 3NF and what is BCNF. Before going to discuss that one, what is 1NF, first normal form? So what is first normal form? If at all, we need to say that if a relation is in first normal form, then it must not contain any multiple values, right? And the tables will be decomposed to remove those redundancies. That is what first normal form. What is second normal form? If the table is in second normal form, then it must satisfy two conditions. What are those two conditions? The table must satisfy. Here I am discussing about 2NF. The table must be in 1NF plus no partial dependency. No partial dependency. That is what 2NF. So these two has been already discussed in our previous sessions. So if you want, you can go and check that one. And now in this session, let us discuss about 3NF and BCNF, Boyce-Codd normal form. So what is 3NF? Third normal form. Third normal form. So a table design is said to be in 3NF if both the following conditions hold. What are the two conditions? So what are those? The table must be in 2NF. That means the table must satisfy 2NF. So if at all the table satisfies 2NF, obviously it is also satisfied 1NF, right? So that is what the point here. The table must satisfy 2NF. And the second thing is, transitive functional dependency of a non-prime attribute should be removed. That means if at all the table contains any transitive dependencies, that must be removed. What is a transitive dependency? Let us take these three functional dependencies first. For example, A tends to B, B tends to C. Then we can say that A tends to C. This is what transitive dependency. This we have already discussed in our previous sessions. So for example, let us deal this one with an example. Okay. So if at all A, that is myself, for example, lecturer. Okay. Or else some teacher. B is one student. Okay. Who is in the class. Who is in the class. So if at all a lecturer and C is one student who is not in the class. He is somewhere outside. Okay. So B is in the class, C is not in the class. Okay. So if I am delivering the lecture to the student who is in the class, at the same day, the next C student is not there in the class. Then what he will do? So this B delivers the lecture, whatever I have told. So the lecture will be delivered by this candidate. Okay, B to this C. Then indirectly I can claim that, so I am only the way to you to deliver the lecture to your friends. That is what? The indirect way of representing. So here indirectly I can say that the teacher delivers lecture to a student who is not in the class also with the help of B. With the help of B. This is what? This is just a basic example that I have represented here. Okay. So this is what transitive dependency. If at all a table or else functional dependencies exist in this format, we have to remove. Why? Because one non-prime attribute cannot determine another non-prime attribute. That is, so what is the result of this one? What is the result of this one? Basically, let us think in a more generic manner, right? So, if a lecturer delivers a lecture to a student who is there in the class, whether he is capable of whatever the points I have represented, okay, whatever the points I have, he may not present to his friend. He may or may not. That is the condition. If at all I used to give 10 important points, by chance he forgot 2. He delivered only 8 points to his friend. Then, right, there is some disturbance, right? Because those 2 important points will be not mentioned to his friend. So that is what the chance. Here B is nothing but one non-prime attribute and C is also, let us consider, this is also non-prime attribute. Why? Because they are students. And A is nothing but a lecturer. Let us consider it is a prime attribute. It is a key. Okay, key. Prime attribute is what? Nothing but a key element in the table. So here lecturer is nothing but prime attribute, key element who delivers lectures to these two students. Okay. So here B is non-prime attribute and C is non-prime attribute. Okay. So if at all a table contains these kind of functional dependencies, we have to remove them. Why? Because one non-prime attribute cannot derive uniquely the another non-prime attribute. That is what the intention of this 3NF, third normal form. So shortly, a table must be in 2NF. What is 3NF? If at all, that it must satisfy two conditions. The table must be in 2NF and there should be no transitive dependency. These are the two steps that we need to keep in mind. So let us discuss these things with example. Let us take this example, a table which contains 3 columns, 3 attributes. Okay, roll number, state and city. Roll number, state and city. So here let us take if at all, this is A, this is B and this is C. Okay. Here I can derive the function attribute A derives B uniquely. A derives B uniquely. See here, A derives B. That means what 1001 derives this state uniquely. 2 AP, 3 Telangana. Okay. 4 AP, 5 Karnataka. And B derives C. From this table only I am writing these functional dependencies. Okay. B derives C uniquely. See. Telangana. State derives city. Telangana, Hyderabad. AP, Guntur. Telangana, Hyderabad. AP, Guntur. Karnataka, Bangalore. So this is also existing. B derives C. Okay. And here key attribute is, for example, roll number. Why? Because what is key attribute? That is nothing but prime attribute. That is what? The key value. It is a super key or a candidate key. Okay. Why? Because it is unique and not null. So this is the key attribute, and here A tends to B. A derives B is also correct. B is also deriving C. B is also derived. By this example, B is also deriving C. But what is our third normal form? One non-prime attribute must not derive another non-prime attribute. Here B and C are non-prime attributes. Why? Because here I am taking roll number as prime attribute. Okay, roll number as prime attribute. B and C are non-prime. How can it can define B derives C? No, right? So this is not in 3NF. We have to make it in 3NF. Okay, to 3NF. So we need to, what is the solution? We need to decompose this table. We need to decompose this table into 2 subtables. So how we can able to decompose? By roll number and state. This is one table, roll number, state, and the another table, roll number and city. This is another table. By splitting this table into 2 subtables, the problem will be solved. Clear? So let us discuss this one. So what is here? The candidate key is nothing but roll number, which I have told now, just now. Okay, the candidate key here will be the roll number. So what is the functional dependencies here? Roll number derives states, state derives city. These are the functional dependencies given. So roll number derives states and state derives C. Here I have shortly I have represented A, B, C. What I have taken, A derives B and B derives C. By this is okay. Why? Because this roll number is a key that derives state. But the second functional dependency, it is not correct. Why? Because one non-prime attribute is deriving another non-prime attribute. That is not at all correct. We have to remove that one. So that is the reason we used to split. We used to split this table. So prime attributes are nothing but roll number. Why? Because here roll number is the candidate key. Whatever the attributes that are there in the candidate key are called as what? Prime attributes. That we have already discussed in the concept of closures, everything. Okay. So what is a non-prime attribute here? Rest of the prime attributes, remaining all are non-prime attributes. So what are the non-prime attributes in this here? State and city. So here 2 non-prime attributes. One non-prime attribute state is deriving another non-prime attribute. That is why we must remove this one. Okay. So here one non-prime attribute is determining another non-prime attribute, that is nothing but state derived city, which is represented by transitive dependency. So we need to decompose the above table into two tables. How we can able to decompose? As I told you, what roll number tends to city and roll number tends to state. That is what the solution here. See, roll number state, roll number city. Now I can able to easily derive. So roll number tends to, this is one functional dependency here, and roll number tends to, this is another functional dependency. So by considering roll number as a prime attribute, that is nothing but a key here. So roll number becomes a prime attribute. So one prime attribute is deriving the non-prime attribute. Again, one prime attribute is deriving non-prime attribute. So this is the reason how we can able to remove transitive dependencies by splitting. So here by taking one more example, what is that one? Here let us take for each and every normal form, we used to define theoretically, like considering some tables and the problematic things also. That is wherever the relation will be given, and from that the given relation we need to verify that the given relation is in 3NF or in 2NF or in 1NF, like that. So the same way here, the conditions, whatever the conditions we need to follow, whether the given relation is satisfies 3NF or not. So these are the 2 points that we need to remember here. So a table, the given relation must be in 3NF if at all it satisfies these 2 conditions. What are those 2 conditions? LHS of all FDs, here FDs means functional dependencies, given functional dependencies. LHS of all given functional dependencies are a super key or a candidate key. That means these LHS are nothing but these parts only, right? So these things must be what? Either super key or candidate key. Super key or candidate key. For all FDs, you have to satisfy this point, or you need to satisfy the second point. RHS of all FDs are prime attributes. Whether LHS must be super key or candidate key, or whether the right sub part, that is RHS, right hand side, must be prime attributes for all FDs. You need to check these 2 points. Clear? So let us discuss this one with a small example. So this is the example, given relation ABCD, and these are the given FDs. AB tends to CD and D tends to A. That is AB derives CD and D derives A. So to find super key, what is the procedure? Whatever the attributes are there in the relation, we need to find the closure. So what is the closure here? We need to include all the attributes A, B, C, D. This is what the closure. And we need to find discarding. Clear? So here AB derives CD. AB from this FD. AB derives CD. We can discard CD. So this will become AB plus A, B, C, D. AB. I have to include AB first here. And AB derives CD from this given FD. So I have include CD. Okay. See, from this one, we can say that any discarding can be done here. No, right? Why? Because we have only one. D tends to A. D derives A. So we can't derive. So we can say that it is a super key. Okay. AB plus is a super key. Okay. From this, what are the subdivisions? That means nothing but the proper subsets of the super key. What? A plus and B plus. Okay. So what is A plus here? A derives A. Next, B derives B. A derives A and B derives B. So from this, we can say that. Why? Because here we doesn't contain any all the values, all the attributes. So we can say that AB is a candidate key. This is what the procedure we have done in our last previous classes. AB is a candidate key. Okay. We have to check AB, whether this AB is in the right hand side of the given FDs. We need to check. So from this, we have represented AB is a candidate key. That is what our first one. Whether AB is there, these 2 are the prime attributes now. Whether these 2 prime attributes are there in the right hand side? Yes, A is there. You have to replace this A with the D. So let us check DB. Now DB closure. DB closure means what here? Here D derives, first we have to include what? D B. We have to include these two. And here D derives A. And from this AB derives CD. So we have to include C. This is what a super key. Now we have to find whether this is a candidate key or not. And we have to find the proper subsets of this one. So what are the proper subsets here? D plus and B plus. D plus means here we have to include D. And D derives A from this one. Okay, this is what. Next, B. B derives uniquely anything? No. So the proper subsets contains no super key, all the attributes. Therefore, DB is also a candidate along with the AB. Okay, that is what. Again, DB. D is any, see here, DB is a candidate key now. So whether D or B is there in the right hand side, see here D is there, but it is not a single D. With the combination of C here it has been derived. Therefore, we must not consider that one. Only the single attribute, wherever the D has in the single attribute in the FD, that FD must be only considered. Okay. So, with this we have concluded AB and DB are candidate keys. AB and DB are candidate keys. Now, for the given relation, AB and DB are candidate keys. So, what are the prime attributes now? What are the prime attributes here? Whatever the attributes that are there in the candidate key. So, here A, B, D are prime attributes. What is the non-prime attribute here? Non-prime attribute is nothing but C. Okay. See here, the given condition AB tends to CD and D tends to A. These are the two FDs given. We need to check for each FD. Whether we have to satisfy the first point or second point. That is what our intention. We need to check the first point or second point. So, here AB tends to CD. In this one, AB tends to CD. LHS is a candidate key? Yes, it is a candidate key. So, okay, it is the functional dependency. Here it is a valid one. Let us consider D tends to A. Why? Because we need not to check the second rule. Obviously, it is OR condition, right? Any one of the rules will be satisfied. What is the second one? D tends to A. So, D tends to A. What is the LHS? LHS is nothing but what here? D. It is a candidate key alone? No. Let us check A. A is a prime attribute. RHS? Yes, it is a prime attribute. So, for all FDs, the given two FDs, we have satisfying these 2 points. Okay, these 2 points. So, I'm again explaining this one. What I have done is, here, AB is the candidate key and DB is the candidate key. So, the prime attributes are A, B, D. Non-prime attributes are C. Okay. Let us consider the first FD, AB. That is what LHS. Whether LHS is a candidate key or not. LHS is AB. AB is a candidate key. Yes, it is a candidate key. So, the condition has been satisfied. The functional dependency is a valid one. Let us consider the second functional dependency, D. Let us consider LHS. D. D is a candidate key. D alone. D alone is a candidate key? No. So, first rule has been not satisfied. Now, let us check for the second rule. What is the second rule here? This RHS must be a prime attribute. So, what are the prime attributes here? A. So, RHS is a prime attribute. Therefore, it is a valid functional dependency. The given relation is in satisfies 3 and F. That is what my point here. So, in this one, in this functional dependency, LHS is candidate key, and in this functional dependency, RHS is what prime attribute. So, the given relation is in 3 and F. That is what my point. So, let us do the second example. Here, let us discuss the short procedure. That is nothing but whatever the missing values are there in the right hand side, those missing values will be taken. See here, whatever the missing values here, D, C, B. Okay. What are the missing values here? Only A. So, we need to find the closure of A. A, B, C, D. This is what A must be included. A derives B, B derives C, C derives D. Okay. This is here. Obviously, we got the super key, but the candidate key is a minimal super key. If at all, we used to consider how we can able to find out the proper subsets of this one. Only single element is there. So, it can be considered as a candidate key. Okay, it can be considered as a candidate key. Why? Because the proper subset of A plus, we can't again refine that one. Clear? It is a nothing but minimal super key only, right? That is here itself, it is a minimal thing. So, we can't again refine that one. So, it can be considered. Whether A is any right hand side? A is not there. So, A itself is a candidate key here. A itself is a candidate key. Why? Because A is not there in the present set. Therefore, so now what is our next procedure? Whether the given relation is in 3NF or not. That is what we have to do. So, what are the given FDs here? First FD, A tends to B. This is what our first FD. Here, A is nothing but a candidate key. Yes, the first FD is valid. Okay. And in B tends to C. Before going to this one, what are prime attributes and what are non-prime attributes? That we have to discuss. What are prime attributes? Whatever the attributes that are there in the candidate key. What are non-prime attributes? Rest of all. B, C, D. These are non-prime attributes. So, for the second FD, B tends to C. Let us check the LHS. LHS is a candidate key? No, it is not a candidate. Now, let us check the RHS. RHS what? It is a prime attribute. Is it a prime attribute? No, it is not a prime attribute. Clear? It is non-prime attribute. RHS must be what here? In the given thing, in the RHS, all FDs must be or prime attributes. So, here C is not a prime attribute. It is a non-prime attribute. Okay. Next. Now, what is the next text here? Is functional dependency. C tends to D. So, here let us check C, LHS. C is a candidate key here? No. Now, let us check the second thing. RHS. RHS is a prime attribute? No, it is not. This is also. Only one functional dependency satisfies. Only A tends to be satisfies the properties of 3NF. Rest of all not satisfying. So, we have to check all the FDs given in the relation. Even one FD doesn't satisfy, that relation is not in 3NF. So, we can conclude that this relation is not in 3NF. This relation is not in 3NF. So, next the Boyce-Codd normal form, BCNF, shortly BCNF, which is also called as 3.5NF. Till now we have discussed the third normal form. Now we are discussing about 3.5NF, which is also called as Boyce-Codd normal form. So, it is nothing but the advanced version of TNF. That is why it is also referred as 3.5NF, which is advanced version of 3NF. So, it is much stricter than 3NF. A table with BCNF must satisfy two properties. What are those? It must be in 3NF. The table must be in 3NF, and for every functional dependency, see, for example, x tends to y, here x should be super key of the table. X should be super key or candidate key of the table. For example, for the given functional dependency A tends to be LHS. A must be super key of the given relation. That is what the Boyce-Codd normal form. Let us discuss with a simple example. So, here employee ID and employee national, these are the 5 attributes that I have taken. And here, let us take the functional dependencies like this. Employee ID derives employee nationality, employee ID derives employee nationality, and employee department derives rest of department type, department number. Employee department, this one. This derives this one and this derives these two. Okay, these are the two functional dependencies given. These are the two functional dependencies given. So, what is the candidate key here? Employee ID and employee. Both combinedly are the candidate key. Okay, both combinedly only we can derive. So, employee ID, employee department are the candidate key. What are the candidate keys here? Employee ID, employee department. Both combinedly are act as a candidate key here. So, what is the rule for this one? The table must be in 3NF, and the second point is, for every given functional dependency, LHS must be a candidate key. So, here, this is the functional dependency. Employee ID is a candidate key? Employee ID. No. Here, candidate key is what? Employee ID plus department, employee department. Clear? So, this employee ID uniquely doesn't derive anything. Clear? So, it is not in 3.5NF. Okay. Now, let us check for this one also. Whether employee department is a candidate key? No. Employee department along with employee ID is a candidate key. So, this is also not in. By considering the given FDs, We can say that what the given relation is not in 3.5 NF. So the table must be decomposed into 2 or more subtables. The table is not in BCNF. So we must decompose into 2 or more subtables. That is what normalization. So here, before going to that one, let us consider this one with a simple example. A derives B, B derives C, C derives A. So here, what we have to do first, we have to find out whether it is, we have to find out the super key, candidate keys of this relation. So what is the missing values here? A, B, C, all are here. So we have to find out A, B, C, closure, A, B, C. Whether A derives B, so we can discard B. So AC plus A, C and A derives B. Whether we can discard C, A derives C. No, C derives A here. C derives A. So we can discard A. So C plus. Okay. So C and C derives A derives B. So itself is a candidate, right? So it is a super key. Now we have to find this, up to this it is a super key. Now we have to find the candidate key, minimal super key. Okay, minimal super key. So how we can find out the minimal super key? Only one attribute is there. So therefore it can be considered as a candidate key also. It can be considered as a candidate key also. So now whether we have to check more candidate keys available in the given relation. So what we have to do for that one? Whether C is available at any right hand side of the given relation. We have to check. C is any C available here, right? So we have to replace it with B, B plus. So what we have to include? B, B derives C, C derives A. This is also a candidate key. Okay. Why? Because it is a super key. Minimal super key is nothing but candidate key. Here minimal means only single element is there. How we can able to? So therefore it is also considered as a candidate key. Super key plus candidate key. Okay. So again, we need to check whether B is available here. Yes, right hand side. It is replaced by A. A plus, now A, we have to include A derives B from this functional dependent, B derives C. This is also a candidate key. Now we have candidate keys what? A, B and C. These are the candidate keys and nothing but prime attributes. Okay. Now we need to check whether this is in BCNF or not. What BCNF? BCNF is nothing but LHS must be a candidate key. Okay, LHS must be a candidate. Now we have 3 candidate keys, A, B and C. These are the candidate keys, right? So what is LHS here in the given FD? It is a candidate key. A is a candidate key. This is a valid FD. B derives C. This is B is also a candidate key, valid FD. What is here? C. C is also a candidate key. This is also a valid FD. So we can say that from this one. So we can say that the given relation is in BCNF. The given relation is in BCNF, Boyce-Codd normal form. So what we have discussed in this session? So in this session we have discussed about what 3NF, third normal form, and 3.5 NF, which is also called as BCNF, which is also called as Boyce-Codd normal form. So what is transitive? What is 3NF here? It must satisfy 2NF and it must we must remove transitive dependency. And in BCNF, what is here BCNF? So for if at all for a given functional dependency extends to phi, X must be a candidate key.